In problem number 20, we are asked to find the volume of the solid which lies below the plane z equals to 12x plus 8y and above the region R in the xy plane bounded by the parabolas y equals to x squared and x equals to y squared. First, let's sketch the region R in the xy plane above which our solid lies. We draw the two parabolas, y equals to x squared and x equals to y squared. It's easy to find their intersection point. It's the point 1, 1. Also, of course, the parabolas meet at the origin, 0, 0. And the region that lies between these two parabolas is the region R that we are looking at. It might also be helpful to visualize the solid. So here to the right I have a picture of the solid in 3 dimensions. We have the region R in the xy plane. We also have a slanted plane z equals to 12x plus 8y schematically, this side. And the solid lies between the region R in the xy plane and the slanted plane z equals to 12x plus 8y. So there's actually a curved parabolic surface bound in the solid on this side right here. All of these curves are parabolas. And then likewise on the back side there are a whole bunch of parabolas as well. And then the top border, the top face of the solid is kind of the region similar to what the bottom region R looks like. Here I have drawn this solid in GeoGebra, which is a really nice software for plotting things in 3 dimensions, freely accessible on the internet, GeoGebra. And so here's the solid in 3 dimensions. By looking at this picture, we'll probably have a good idea what it looks like. And now how do we calculate the volume of the solid? Well, the idea is to simply express this volume as a double integral of the function z over the region R. Remember that that's one of the interpretations of double integral, that it calculates the volume of a solid that lies above the region of integration and below the graph of the function, at least in the case when the function takes non-negative values. Okay. So here's this integral. The volume V of the solid can be calculated as a double integral of our function z, 12x plus 8y, over the region R in the xy plane. How will we calculate this integral? Well, of course we will use iterated integration, and we have a choice of whether to integrate over x first or over y. Doesn't particularly matter in this case. Let's say I want to integrate over x first, then we fix the value of y and consider the horizontal cross sections of our region. The left hand point of this of such cross section lies in the parabola x equals to y squared. The right hand point lies on the parabola y equals to x squared. So if we wanted to know, and we do want to know the right endpoint of this cross section, we need to solve this equation y equals to x squared for x. Of course, we will find that x equals to square root of y. And so accordingly, our first integration over x will have the limits from y squared to the square root of y. And what are we integrating? We're integrating 12x plus 8y with respect to x. Once we're finished integrating over x, the result will be a function of y. And now let's see what the range of y coordinates in our region is. You see that the region lies between the lines y equals to 0, that's the x-axis, and y equals to 1. And so the range of y values for the points inside our region is between 0 and 1. And that gives us the limits of integration for the second integration, which will be integration over y. From 0 to 1 dy. And now it's a fairly simple matter to finish this integration. When we integrate over x, 8y is a constant. So the integral of that constant will be that constant times the length of the integral of integration. And the antiderivative of 12x will be 6x squared. Uh, 6x squared will have to be evaluated at the endpoints of the integral of integration. And then plus, as I mentioned earlier, the integral of the constant term 8y will be that constant term 8y multiplied by the length of the integral of integration, which is square root of y minus y squared. Y. Okay. Now let's calculate what happens when we use the antiderivative 6x squared of the function 12x and plug in the limits of integration, take the difference. We're going to get 6 square root of y squared minus 6y squared squared. And then I'm going to distribute 8y to the two terms in parentheses that 8y is being multiplied by. So plus 8y times square root of y, and then minus 8y times y squared dy. Let's now simplify this. It will also help to write radicals as fractional powers of y. For the first term, where square root of y is being squared, we get 6y. And we have minus 6y to the fourth. Next, we have 8y times square root of y. Square root of y is y to the power 1/2, so looking at this term here, 8y times y to the power 1/2. And when we multiply two powers of y, the exponents get added, so we get 8y to the power 3/2 minus 8y cubed. And that is the function that we need to integrate over y. We use the power rule to find the antiderivative. It will be 3y squared minus 6y to the 5th over 5 plus 8y to the power 5 halves divided by 5 halves. And finally, don't have that much space left, unfortunately. Finally, minus 2y to the fourth. Okay. Let's see if I have space up here. Yeah, I have a lot of space up on the board, so let me actually go to the top. So from here, continuation will be here. So this is the antiderivative that we've found, and it has to be evaluated at the endpoints. Now, when we plug in, instead of y0, the whole thing turns into 0. And then when we plug in y equals to 1, all the powers of y turn into 1. So it's not going to be too complicated to calculate this. 3 minus 6/5. And then we'll have 8 divided by 5 halves. That's going to be 16/5. And then finally we have minus 2 to the y, minus 2 times 1 to the fourth. So it's just minus 2. And 16/5 minus 6/5, that's 10/5, so it's positive 2. And so we get 3 plus 2 minus 2, 3 overall. The volume of this solid is 3.